Light, reflection and refraction. We all know that light is a form of energy. It travels in a straight line. In this chapter, we are going to study the reflection and refraction of light. What is reflection of light? When a light ray strikes a smooth polished surface like mirror, it bounces back. It is called as reflection of light. We can study the reflection of light with the help of mirrors. Mirror is an opaque object with shiny reflective surface. It is because of the reflection of light we will be able to see our images in mirrors. What is refraction of light? When a light ray passes from one medium to another medium, its traveling speed changes and results in change of its direction. This phenomenon is called refraction of light. A straw in a glass appears to be bent. This is due to refraction of light. We can study the refraction of light with the help of lens. Lens is a transparent object usually made of glass. Eyeglasses are the examples of lenses which use in our day-to-day life. First, let us study the reflection of light with the help of mirrors. This is a plane mirror. When a light ray strikes a plane mirror, it gets reflected back. According to the laws of reflection, the angle of reflection is equal to the angle of incidence. Image formation. Plane mirrors create virtual images that appear to be located behind the mirror at the same distance as the object in front of the mirror. These virtual images are not real. That means they cannot be projected onto a screen. They are formed by the apparent intersection of reflected light rays when extended backward. Size and magnification. The size of the image in a plane mirror is the same as the size of the object. There is no magnification, means that objects in a plane mirror appears to be the same size as they are in reality. Laterally reversed. The images formed by plane mirrors are laterally reversed, also known as left-right reversed. This means that if you raise your right hand in front of a plane mirror, your image will appear to raise its left hand. Now, let us understand the reflection of light by spherical mirrors. A spherical mirror is a curved mirror and it forms the pot of a sphere. Spherical mirrors are of two types. 1. Convex mirrors and 2. Concave mirrors. A convex mirror is a type of a spherical mirror that has an outward curved reflective surface. A concave mirror is a type of a spherical mirror that has an inward curved reflective surface. To understand reflection by a spherical mirror, we need to know certain terms. Pole. The center point of the reflecting surface of a spherical mirror is called pole. It lies on the surface of the mirror. Pole is denoted by letter P. Center of curvature. The center of curvature is the center of the imaginary sphere from which the spherical mirror is derived. It lies behind the mirror in case of a convex mirror and lies in front of the reflecting surface of a concave mirror. It is represented by the letter C. Radius of curvature. The radius of curvature or of a spherical mirror is the radius of imaginary sphere of which mirror is a part. Principal axis. The line joining pole and center of curvature is called principal axis. We should remember that the principal is normal to the mirror at its pole. That means at the point of pole, the angle between the plane of the mirror and the principal axis is 90 degrees. Principal focus. If a number of light rays parallel to the principal axis are falling on a concave mirror, they all meet or intersect at a point on the principal axis of the mirror. This point is called the principal focus of the concave mirror. In case of a convex mirror, the reflected rays appear to come from a point on the principal axis. This point is called the principal focus of the convex mirror. The principal focus is represented by the letter F. Focal length. The distance between the pole and the principal focus of a spherical mirror is called the focal length and it is represented by the letter small f. Aperture. The diameter of the reflecting surfaces of the spherical mirror is called its aperture. In this chapter, we are discussing about the spherical mirrors whose aperture is smaller than their radius of curvature. Let us see the relation between the radius of curvature and the focal length. The relationship between the radius of curvature r and the focal length f of a spherical mirror is as follows. For spherical mirrors with small apertures, the radius of curvature is found to be equal to twice the focal length. We write it as r equal to 2f or f equal to r by 2. This means that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. Representation of images formed by spherical mirrors using ray diagrams. Rules for making ray diagrams. Parallel ray rule. For a concave mirror, if a light ray passes parallel to the principal axis, after reflecting, it passes through the focal point F. For a convex mirror, if a light ray passes parallel to the principal axis, after reflecting, it appears to come from the focal point F behind the mirror. Focal ray rule. For a concave mirror, if a light ray passes through principal focus, after reflection, it emerges parallel to the principal axis. For a convex mirror, if a light ray is directed towards the principal focus, after reflection, it emerges parallel to the principal axis. Center of curvature ray rule. For a concave mirror, if a light ray goes from the object to the center of curvature, after reflection, it retraces its path back to the center of curvature. For a convex mirror, if a light ray is directed in the direction of center of curvature, after reflection, it retraces its path back. 4. A ray incident oblique to the principal axis towards pole of the mirror is reflected obliquely on the concave mirror or a convex mirror, the incident and reflected rays making equal angles with the principal axis. First, let us draw some ray diagrams. Image formation by a concave mirror for different positions of the object. Case 1. If the position of the object is at the infinity, the position of the image will be at the focus F. The size of the image is highly diminished and point-sized. The nature of the image is real and inverted. Case 2. If the position of the object is beyond C, the position of the image will be between F and C. The size of the image is diminished. The nature of the image is real and inverted. Case 3. If the position of the object at C, the position of the image will be at C. The size of the image will be same as object. The nature of the image is real and inverted. Case 4. If the position of the object is between C and F, the position of the image will be at beyond C. The size of the image will be enlarged. The nature of the image is real and inverted. Case 5. If the position of the object is at F, the position of the image will be at infinity. The size of the image will be highly enlarged and the nature of image is real and inverted. Case 6. If the position of the object is between P and F, the position of the image will be behind the mirror. The size of the image will be enlarged and the nature of image is virtual and direct. Uses of concave mirrors. Concave mirrors are used as shaving mirrors, dentist mirrors. They are also used in the reflectors of torchlights and vehicle lights. Now, we will see the image formation by concave mirror. Here we consider only two positions of the object for studying the image formed by concave mirror. Case 1. If the position of the object is at infinity, the position of the image will be at the focus behind the mirror. The size of the image is highly diminished and point-sized. The nature of the image is virtual and direct. Case 2. If the position of the object is between infinity and the pole of the mirror, the position of the image will be between P and F behind the mirror. The size of the image is diminished. The nature of the image is virtual and erect. Uses of convex mirrors. They are used as rear view mirrors in vehicles because they always forms an erect image and have wider field of view as they are curved outwards. Sign convention for reflection by spherical mirror. The sign convention for spherical mirrors is a set of rules used to determine the sign, either positive or negative, of various distances and quantities involved. This convention is important for calculating the image distances, object distances, and to find magnification. Object placement. The object is always placed to the left of the mirror. indicating that the light from the object approaches the mirror from the left side. Measurement from the pole. Distances parallel to the principal axis are measured from the mirror's pole. The pole is the point where the mirror surface intersects the principal axis. Direction of measurement. All distances measured to the right of the origin along the positive x-axis are considered positive, while those measured to the left of the origin along the negative x-axis are considered negative. This helps in determining the position of the object and image relative to the mirror. Height above the principal axis. Distances measured perpendicular to and above the principal axis along the positive y-axis are considered positive. This is used to determine the heights of the objects and images above or below the principal axis. Height below the principal axis. Distances measured perpendicular to and below the principal axis along the negative y-axis are considered negative. This convention ensures that heights below the principal axis are assigned negative values. These sign conventions are fundamental for analyzing and solving problems related to spherical mirrors. Mirror formula and magnification. The mirror formula is particularly useful for determining the position and characteristics of an image formed by a mirror. The mirror formula is a fundamental equation used to relate the object distance u and the image distance v and the focal length f of a spherical mirror. It is expressed as 1 by v plus 1 by u is equal to 1 by f, where f is the focal length of the mirror, v is the image distance, means the distance from the mirror to the image, and u is the object distance, that is the distance from the mirror to the object. Magnification. Magnification refers to the ratio of an image to the height of an object. It is denoted by letter m. That means it is the comparison of the size of the image with respect to the size of the object. That is, height of the image h dash by height of the object h, means m is equal to h dash by h. The height of the object should be taken as positive since it is usually placed above the principal axis. The height of the image should be taken as positive if the image is virtual and should be taken negative if the image is real. That means if the image is on the side of the object. We can also find magnification by comparing the image distance and object distance. We know that image distance means the distance between the mirror and the image, and object distance means the distance between the mirror and the object. So magnification is equal to image distance by object distance. That means m is equal to minus v by u. Refraction of light. Refraction is the change in the direction of light passing obliquely from one medium to another medium. Refraction occurs due to change in the speed of light as it enters from one transparent medium to another. The speed of light is more in air, whereas the speed of light in water is less compared to air. So the light ray, when it enters from air to water, it bends towards the normal. The refracted ray is closer to the normal when compared to the incident ray. In our day-to-day life, we see different phenomena like pencil appears displaced when it partly immersed in glass of water. In the same way, a lemon kept in water in a glass tumbler appears to be bigger than its actual size. The letters appears to be raised when seen through a glass slab placed over it. These are all because of refraction of light. These observations tell us that light does not travel in the same direction in all media. Refraction through a rectangular glass slab. Let us take a glass slab and pass a light ray obliquely from one of its sides. The light ray bends towards the normal, and when it emerges out from the glass slab, it bends again and moves away from the normal. Here we can observe that the angle of incidence at the air glass interface is equal and opposite to the angle of emergence at the glass air interface. This is why the emergent ray is parallel to the incident ray. Laws of refraction of light. 1. The incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. 2. The ratio of sine of angle of incidence to the sign of angle of refraction is a constant for the given pair of media. This law is also known as Snell's law of refraction. If I is the angle of incidence and r is the angle of refraction, then sin I by sin r equal to constant. Refractive index. The refractive index of a medium is a measure of how much the speed of light is reduced when it passes through that medium compared to its speed in vacuum. It is a dimensionless quantity, and a higher refractive index indicates a slower speed of light in that medium. Light travels faster in vacuum with a speed of 3 into 10 to the power of 8 ms to the power minus 1. In air, the speed of light is only marginally less compared to that in vacuum. It reduces considerably in glass or in water. The value of refractive index for a given pair of media depends upon the speed of light in the two media. A ray of light traveling from medium 1 into medium 2. Let V1 be the speed of the light in medium 1 and V2 be the speed of the light in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. This is usually represented by the symbol n21. This can be expressed as n21 equal to speed of light in medium 1 by speed of light in medium 2. That means V1 by V2. The refractive index of medium 1 with respect to medium 2 is represented as n12. It is given as n12 equal to speed of light in medium 2 by speed of light in medium 1. That means V2 by V1. If medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to vacuum. This is called the absolute refractive index of the medium. It is simply represented as n2. If c is the speed of light in air and v is the speed of light in the medium, then the refractive index of the medium nm is given by nm equal to speed of light in air by speed of light in medium, that is c by v. Different materials have different refractive indices. For example, the refractive index of water is approximately 1.33, while the refractive index of diamond is approximately 2.42. Now let us see the refraction by spherical lenses. A transparent material bound by two surfaces of which one or both surfaces are spherical forms a spherical lens. They can be either convex lens or concave lens based on their shape and refractive properties. A convex lens, also known as converging lens. It is a transparent material with curved surfaces. It is thicker at the center and thinner at the edges. Convex lenses are designed to converge or focus parallel incident light rays to a single point called the focal point. A concave lens, also known as diverging lens, is a transparent optical device with curved surfaces that curve inward like a cave. Concave lenses are thinner at the center and thicker at the edges. These lenses are designed to cause parallel incident light rays to diverge away from the virtual focal point. A lens has two spherical surfaces. Each surface forms a part of a sphere. The center of these spheres is called center of curvature. Principal axis. An imaginary straight line passing through the two centers of curvatures of a lens is called its principal axis. Optical center O. The central point of a lens is called optical center. Aperture. Effective diameter of the circular outline of a spherical lens is called its aperture. Principal focus F. The point where the rays parallel to the principal axis meet after refraction is called principal focus. A lens has two spherical foci. Focal length F. The distance of principal focus from optical center. Rules for the ray diagram of spherical lens. A light ray which is parallel to the principal axis after refraction will pass through the principal axis in case of convex lens and will appear to be coming from principal focus in case of concave lens. Light rays passing through the convex lens or directed towards the focus in concave lens will emerge parallel to principal axis. A ray directed to the optical center will emerge out undeviated in case of both convex and concave lens. Image formation by convex lens. Case 1. If the position of the object is at infinity, the position of the image will be at the focus f2 and the relative size of the image is highly diminished and point-sized. The nature of the image is real and inverted. Case 2. If the position of the object is at beyond 2f1, the position of the image will be between f2 and 2f2. The relative size of the image is diminished. The nature of the image is real and inverted. Case 3. If position of the object is at 2f1, the position of the image will be at 2f2. The relative size of the image is same. The nature of the image is real and inverted. Case 4. If position of the object is at f1 and 2f1, the position of the image will be at beyond 2f2. The relative size of the image is enlarged. The nature of the image is real and inverted. Case 5. If position of the object is at focus f1, the position of the image will be at infinity. The relative size of the image is infinitely large and highly enlarged. The nature of the image is real and inverted. Case 6. If position of the object is between focus f1 and optical center O, the position of the image will be on the same side of the lens as the object. The relative size of the image is enlarged. The nature of the image is virtual and erect. Let us now study the nature, position and relative size of the image formed by a concave lens. Case 1. If position of the object is at infinity, the position of the image will be at the focus f1. The relative size of the image is highly diminished and point-sized. The nature of the image is virtual and erect. Case 2. If the position of the object is between infinity and optical center O of the lens, the position of the image will be between focus and optical center O. The relative size of the image is diminished. The nature of the image is virtual and erect. Sign convention of spherical lens. The sign convention of the spherical lens is same as the one used for spherical mirrors. We apply the same rules for signs of distances except that all measurements are taken from the optical center of the lens. In the sign convention of spherical lens, the focal length of a convex lens is positive and that of a concave lens is negative. Lens formula. This formula gives the relationship between object distance u and image distance v and the focal length f. The lens formula is expressed as 1 by v minus 1 by u equal to 1 by f. The magnification m of a spherical lens is a measure of how much the lens magnifies or reduces the size of an object as it forms an image. Magnification is calculated using the following formula: m equal to h dash by h. Magnification is represented by the letter m. If h is the height of the object and h dash is the height of the image given by a lens. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by m is equal to h dash by h equal to v by u, where m is the magnification of the lens, v is the image distance, means the distance from the lens to the image, and u is the object distance, means the distance from the lens to the object. Power of lens. The power of a lens is a measure of its ability to bend light. It is represented by the letter P. The power P of a lens of focal length f is given by P equal to 1 by f. The power of a lens is measured in units called diopters d. P is the power of the lens in diopters d. F is the focal length of lens in meters m. Positive and negative powers. A lens with a positive power is called a converging lens, which focuses light rays to a point. Convex lenses have positive powers. A lens with a negative power is called diverging lens, which causes light rays to spread out. Concave lenses have negative powers. This is all about the reflection and refraction of light.